In this lesson, we're going to explore the reactions of carboxylic acids and acid derivatives, focusing on simple acyl substitution. The primary mode of reactivity for carboxylic acids and acid derivatives is acyl substitution. Acyl substitution is the replacement of an atom or a group on the carbonyl by a nucleophile. All acid derivatives share a common substructure. Each carboxylic acid derivative is simply a carbonyl attached to some kind of an electronegative heteroatom, an oxygen, a nitrogen, or a halogen. Those heteroatoms can serve as a leaving group in what is essentially a nucleophilic substitution. In the generic example here, we see the leaving group represented by X. Acyl substitution is simply the replacement of that leaving group with some nucleophile. This reaction should be reminiscent of the other nucleophilic substitutions you've seen before, the SN1 and SN2 reactions. Acyl substitution is essentially the same thing, except now it's taking place on a carbonyl. And because the carbonyl carbon is sp2 hybridized, we know that SN1 and SN2 mechanisms are not a possibility. SN1 and SN2 reactions only occur on sp3 hybridized carbons. The mechanism for simple acyl substitution varies based on the type of nucleophile used. The simplest variation involves the use of a negatively charged nucleophile. In the first step, the nucleophile attacks the electrophilic carbonyl carbon, breaking the carbon-oxygen pi bond. In the second step, the pi bond reforms, expelling the leaving group. The use of an uncharged or neutral nucleophile adds one additional step. The mechanism starts off in the exact same way. The nucleophile attacks the electrophilic carbon of the carbonyl, breaking the carbon-oxygen pi bond. In the second step, a base removes a proton from the nucleophilic atom. In the last step, the carbonyl pi bond is reformed, expelling the leaving group. You can see that the mechanism for nucleophilic substitution using a neutral nucleophile is essentially the same as using a negative nucleophile. The only difference is that we've introduced that deprotonation step in the middle. Before we can begin looking at specific acyl substitution reactions, we need to have an understanding of the relative reactivities of all carbonyl types. The relative reactivity of carboxylic acid derivatives are largely dependent on the stability of the leaving group present. In general, the better the leaving group, the more reactive the carbonyl. This exactly mirrors what we learned with the other forms of nucleophilic substitution, the SN1 and SN2 reactions. Remember that a weaker or more stable base will be a better leaving group. Think about the leaving groups that are attached to the various types of carboxylic acid derivatives. The leaving group on a carboxylic acid would be the hydroxy group. The leaving group on an acyl halide would be a halide. The leaving group on an anhydride would be a carboxylate. The leaving group on an ester would be an alkoxide. And the leaving group on an amide is a negative nitrogen, which is unfortunately also referred to as an amide. Think of sodium amide. If we order these leaving groups according to their relative stabilities, we get the trend shown here. Remember that large atoms can stabilize charge extremely well, making bromide the best leaving group. This is followed by chloride, a smaller yet rather large atom. The remaining leaving groups involve negatively charged oxygens or nitrogens. Oxygen and nitrogen are the same size. We know that oxygen is more electronegative than nitrogen, meaning it will stabilize a negative charge better. This makes the negative nitrogen leaving group from an amide the worst leaving group. The alkoxy group, which would serve as a leaving group on an ester, and the hydroxy group, which would serve as a leaving group on a carboxylic acid, are roughly the same in stability. The carboxylate leaving group seen from an acid anhydride is resonance stabilized, making it a superior leaving group to the alkoxy and hydroxy groups. Using the relative stabilities of these leaving groups, we can predict the relative reactivities of all carboxylic acid derivatives. The figure included here shows the relative reactivities of all of the major types of carbonyl compounds. This figure shows aldehydes and ketones in addition to the acid derivatives. Just remember that aldehydes and ketones undergo acyl addition and not acyl substitution. What we see is that acyl halides are the most reactive carbonyls, followed by acid anhydrides, then aldehydes, ketones, and esters. But then we see a bit of a surprise. Based purely on leaving group stabilities, we would predict that carboxylic acids would fall next, followed by amides. It turns out that carboxylic acids are often the least reactive of all carbonyl types, at least in simple uncatalyzed acyl substitutions. You'll see why this is the case in a later lesson. For now, you just need to remember that carboxylic acids are a bit of an anomaly and fall last in the relative ordering of reactivity. Traditionally, Acyl substitution reactions are learned by stepping through each individual functional group and discussing the reactions specific to that type of compound. This approach is tedious and unnecessary. It also incorrectly implies that the reactions are somehow unique to the specific functional groups. We're going to take a greatly simplified approach, an approach that relies on an understanding of the relative reactivities of the various carbonyl types. Remember that acyl substitution is a type of nucleophilic substitution. And just like SN1 and SN2 reactions, acyl substitutions are reversible. The reverse of an acyl substitution is simply a different acyl substitution. Rather than memorizing dozens of reactions for the various functional groups, we can use our understanding of reaction equilibrium to predict the outcomes of any acyl substitution. As in any reaction, equilibrium will always favor the side of greater stability. In a nucleophilic substitution, equilibrium will favor the displacement of the better, more stable leaving group. This means that simple, direct acyl substitutions will favor products when the reaction leads to a less reactive carbonyl type. Let's take a look at a few examples that demonstrate this. In the first example, we see an acyl halide reacting with a carboxylate. The carboxylate will act as the nucleophile and displace the halide as the leaving group. The result is the formation of an acid anhydride and chloride. We can predict this to be a productive reaction. Equilibrium will favor products, shifting to the right. The reverse reaction would be the treatment of an acid anhydride with chloride as a nucleophile, forming a carboxylate and an acyl halide. We know that chloride is a better leaving group than a carboxylate, and because of that, we know that acyl halides are more reactive than acid anhydrides. Equilibrium will favor the side with more stable, less reactive species. In this case, shifting to the products on the right. In the second example, we see an acyl halide reacting with water, forming a carboxylic acid and chloride. We can again predict this reaction to be productive, favoring products. The simplified explanation is that acyl halides are more reactive than carboxylic acids. And as we just stated, these simple direct acyl substitutions will favor products when the reaction leads to a less reactive carbonyl. The product carboxylic acid is less reactive than the reactant acyl halide, so the reaction works. In the last example, we see a carboxylic acid reacting with ammonia to form an amide and water. Remember that carboxylic acids are the anomaly. They're actually the least reactive of all the carbonyl types. This means that the product amide is more reactive than the starting carboxylic acid. We predict that equilibrium will favor the left, making this an unproductive reaction. Using this approach, you can predict the outcome of nearly any simple, uncatalyzed acyl substitution. The reactions of carboxylic acid derivatives with organometallic reagents deserve special consideration. Many carboxylic acid derivatives undergo a tandem acyl substitution addition when reacted with organometallic reagents. If we look at the example, we see an ester treated with a Grignard reagent. The strongly nucleophilic organometallic reagent will induce acyl substitution, replacing the methoxy group with a methyl group. This results in the formation of a ketone. And remember that ketones are more reactive than most of the acid derivatives. As this ketone is produced, it reacts with the Grignard reagent more quickly than the original ester. As it's formed, the ketone undergoes an acyl addition with a second equivalent of the Grignard reagent, ultimately forming an alcohol. The reaction of a ketone with a Grignard reagent is something we've seen before. Because the ketone intermediate is more reactive than the starting material, the reaction cannot be stopped after a single addition of the Grignard reagent. In order to avoid a mixture of products, an excess of Grignard reagent is used. The net result is the formation of an alcohol and two new carbon-carbon bonds. The reactions of esters and acyl halides is a synthetically useful way of producing tertiary alcohols. Up to this point, we've kind of neglected one of the acid derivatives, specifically nitriles. Nitriles are quirky. They're not really even carbonyl compounds. And unlike the other acid derivatives, they lack a leaving group. Nitriles are similar to the other acid derivatives in the sense that the functionalized carbon has 3 bonds to an electronegative atom, in this case, 3 bonds to the same nitrogen. Unlike other acid derivatives, nitriles can react with one equivalent of an organometallic reagent to form a ketone. When an organometallic reagent attacks the electrophilic carbon of a nitrile, a negatively charged imine anion is formed. Because nitriles lack a leaving group, this negative charge remains on the intermediate. That negative charge prevents another organometallic reagent from attacking. The negative charge in the intermediate simply repels the negative charge in the organometallic reagent. Quenching the reaction with acidic water forms an imine, which is then hydrolyzed to the ketone. This reaction is a synthetically useful way of creating a carbon-carbon bond that results in the formation of a ketone. The reactions of carboxylic acid derivatives with hydride donors also deserve special consideration. All carboxylic acid derivatives undergo a tandem acyl substitution addition reaction when reacted with hydride donors. In the first example, we see an ester treated with lithium aluminum hydride. The ester undergoes an acyl substitution, and the methoxy group is replaced by a hydrogen. This results in the formation of an aldehyde. And remember, aldehydes are more reactive than most of the acid derivatives. As the aldehyde forms, it reacts more quickly with the lithium aluminum hydride than does the starting ester. The aldehyde intermediate reacts with a second equivalent of lithium aluminum hydride, forming a primary alcohol. This is the exact same phenomenon we observed in the reactions of carboxylic acid derivatives with organometallic reagents. In the second example, we see an amide reacting with lithium aluminum hydride. The nitrogen-containing acid derivatives, that is, amides and nitriles, result in the formation of an amine when treated with lithium aluminum hydride. A simple way to remember this is that oxygen is a better leaving group than nitrogen, and so the oxygen leaves and the nitrogen stays. In the third example, an ester is treated with sodium borohydride. Remember that sodium borohydride is a much weaker source of hydride than is lithium aluminum hydride. Most carboxylic acid derivatives are simply too unreactive to undergo a reduction with sodium borohydride. In general, it's best to use lithium aluminum hydride when reducing acid derivatives and sodium borohydride when reducing aldehydes and ketones.